I want to welcome everyone for attending this webinar. My name is Ali Hajbabaie. I am an associate professor in the Department of Civil, Construction and Environmental Engineering at NC State University. And we have Dr. Elefteriadou from University of Florida and Dr. Mohammed Hadi from Florida International University. And today, the three of us want to talk about some of the findings of the research that we have been working on over the past couple of years on integrated corridor management. And I want to say it was a pleasure to work with this group of people. This project was funded by STRIDE, which is a regional university transportation center. It has 10 member universities, and this project was one of the projects that was funded there. And STRIDE is a Region 4 regional UTC. Before we get into the details of this talk, I want you to meet the team. And here you see an excellent group of students that worked on this project, did most of the heavy lifting, and we have Abdullah and Rasul from NC State, Leonida from University of Florida, and Atika and Hector from Florida International University. So let's start with this research. And what you see on this slide is a freeway that is pretty much congested, and you see an on-ramp that is heading to this freeway, and you see on-ramp metering signals on this on-ramp. And what we have here is that the freeway is pretty much congested. The on-ramp is also congested, and what can happen in situations like this is that we are gonna meter traffic on the on-ramp to help the flow on the freeway, but what happens is that the queue is gonna spill back from the on-ramp to the interchange and then to upstream intersections, and the traffic congestion on the arterial street could be really bad. So what are some solutions that can help us to mitigate this situation? First, we need to be able to predict the start of queue spillback from on-ramp to the upstream intersections. And when we can do that, we can either flush the traffic on-ramp. That's something that has been used. And the issue with that is that the traffic situation on the freeway main line could get really worse, because now we don't control any of the traffic that is going from the on-ramp to the freeway. We can use upstream intersection signals to manage traffic more efficiently so that we can distribute the queue that was on the on-ramp and was spilling back to upstream intersections on the arterial street, or we can go another step forward and use upstream intersections signals in coordination with ramp metering signals and pretty much do an integrated corridor management operations there. So let's see what were the objectives of this project that we did together. So we wanted to develop an integrated corridor management methodology. That was like our goal or our overarching objective. And to achieve that, we went through three other objectives. One was to develop an optimization model for cooperative traffic signal and ramp metering control. And when we developed this model, we integrated in vSIM because we wanted our results to be more representative of what happens in an actual corridor. We also developed a procedure for adjusting arterial signal control to reduce on-ramp demand. And this procedure is like a step-by-step procedure that allows you to work with signal timing on the upstream intersection so that you can manage the demand better on the on-ramp. And we also wanted to develop a method to forecast queue spillback from on-ramp before it occurs. And that's really critical to all the two methods above so that you can activate them to prevent the spillback. So I'm going to go through the first bullet point here, and Dr. Elefteriadou is going to explain or introduce the second one, and Dr. Hadi is going to go through the third bullet point here. So let's start with cooperative traffic signal and ramp metering control. And the way that we address this problem was that we tried to develop an optimization model that does this control method. So we formulated an optimization model. It's a mixed integer nonlinear program. So what that means is that we have decision variables that are continuous and also integer, and we have a lot of nonlinearity in that model. So that pretty much makes the model complex. That's what I want to get at here. We use the cell transmission model network loading concept here. And what it does is that it takes a link and divides it to homogeneous cells. By that, we reduce the complexity of the problem. And then it has a logic to move vehicles from one cell to the other cell. This optimization model has an objective. Our objective here, or objective function here, was to maximize the throughput in the corridor, maximize the number of completed trips. And we have the option of giving different weights to the trips that are completed on the freeway, on arterial, and side street. And we have a number of constraints here. We have flow conservation constraints. So we don't want to lose vehicles when they move from one cell to the next one. We have flow feasibility constraints. So flow always needs to be below capacity. We have signal timing constraints and also ramp metering constraint. So I'm not going to go to the math here, but this is really the concept behind the model that we used here. And to solve this model, we used model predictive control. So this is an approach that is widely used in control problems. So what it does is that it observes the current state of traffic. And we do that in VSIM. VSIM is the microsimulator that we use here. So we go to that and we observe the state of the traffic. Based on that, we are going to predict traffic state over a prediction horizon. And that horizon usually is in the order of a few minutes. Here, we were looking 5 minutes ahead of the current time. Then we use our optimization model, we solve it, and what that gives us is signal timing on all the signalized intersections and also timing of the ramp metering signals. And what we do is that rather than going and implementing those solutions in VSIM for the entire horizon, we go and we implement the solutions that we found for our immediate next time step. That's in the order of seconds. It could be 6 seconds, 10 seconds or so. And then this process is repeated over and over. So we go to VSIM, we gather data, we optimize, we implement, and we continue this over the entire study period. So we took this and we applied it to a case study corridor that we have in San Mateo in California. This is US 101, and we are looking at 1.6 miles of the freeway and also 1.6 miles of a arterial street that has an interchange with this freeway. And our main focus here was on the northbound of the freeway because we have two on-ramps, one here, that we can meter traffic using RAM metering signals. And this is coming from a Federal Highway Administration project that created VSIM model and collected data here. And also there are some ramp metering signals implemented in the simulation model here. So we created 5 scenarios and tested those in VSIM. The first one was the existing system with no metering, and the existing system had metering implemented, but we wanted to remove those metering signals to see what we are going to observe if there was no ramp metering implemented there. The second scenario that we tested was the existing system with original ramp metering plans that was there. Our third scenario was to optimize metering rates there using our own algorithm. The fourth scenario was only optimize signal plans on the intersections on the arterial, and we did that on intersection 1, 2, 3, and intersection 4 here. And the last thing that we did was integrated control. So at the same time that we are optimizing timing of signals on these 4 intersections, we are also optimizing metering rates on these 2 on-ramps. And we we compared the results of these 5 scenarios to each other, and I'm gonna show them to you in the next slides. And for all of these, the demand was identical for all these 5 scenarios. So on this table, on each column, you see one of the 5 scenarios. On each row, you see a traffic performance measure. And I'm going to start with throughput because this was our objective function. And you can see that when we go from the existing system with no metering to the existing system with original metering and so on, the throughput is getting better. And that's what we expected. And our expectation is to get the highest throughput with integrated control. But when you look at these numbers, they are not like significantly different in terms of throughput. But when you look at other performance measures, such as average delay, you can see significant differences and how pretty much using signals could help. So when you don't use signals, we are in the order of 70-some average delay per vehicle, second per vehicle. And when you start using or start controlling the signals, you see a huge dip in those average delays. And one main reason for that is that traffic condition on the arterial street was not good. And when we started using these signals, we could achieve huge savings. And the reason that we had the issue on the arterial was the queue that was spilling back from the on-ramp to the arterial and creating a mess on the arterial. And optimizing signal plans can help, and integrated control also can help to reduce that delay on that arterial. So there are a lot of other numbers here. I don't want to get into them, but I want to look into some other numbers on this network that we have been looking into. So we want to look into eastbound arterial. We want to look into on-ramp number 2, which is this on-ramp. And we also want to look into northbound freeway, this direction. Okay, and I'm going to show you some graph to see how things change when we go from one scenario to the other one. So here on the y-axis, we are looking at the average delay. And again, on the x-axis, I have our different scenarios. And what you see here is that when we don't do any metering, we have the highest average delay on the main line. And that's what we expect, right? And when we do some sort of metering, this is the original metering, that average delay is reduced. We see the opposite trend on the arterial. So the delay on the arterial significantly increased when we have metering. And these are both original metering. Now, when we did our own metering, what is happening is that we are reducing the delay on the arterial street, and we are reducing the delay on the northbound compared to no metering. But the original metering that was there worked better on the freeway. But the reason that we have higher delay on the freeway here is that still our metering was looking at the entire system. So it was trying to improve not only the freeway, but freeway and arterial as a system together. So now when we move to optimal signal plans, you can see that we have a huge reduction in average delay on the arterial street. we are reducing the delay on the freeway compared to our metering and to the original system with no metering, but we have slightly higher travel time, average delay on the freeway main line. And when we go to integrated control, compared to signal plans, our delays on the freeway is a little bit lower, on the side street is a little bit higher. Not on the side street, on the arterial street. So let's look into the last two strategies, optimal signal control and integrated control. And here, what you see is that integrated control is reducing the delay on the northbound of the freeway, right? But then there is some increase on the arterial street. So if I want to give you some numbers, integrated control reduced the arterial delay by almost 80%. But that was at the expense of 5% increase on freeway delay. These numbers for optimal signal control was 88% reduction on the arterial street delay at the expense of 19% increase on freeway delay. So this tells me that integrated control provides a better balance in traffic operations on the northbound, on the freeway and on the arterial street, at least in the case study that we analyzed here. And we have the option of changing some weights so that this balance changes. So this is one of the settings that we looked into. So some of the key findings that we had here, one was, of course, we developed this method that could control signal timing parameters and metering rates in cooperation with one another. And the integrated control reduced average delays, average stops, and travel time by 33%, 36%, and 60%. And this is compared to existing control that was implemented in the VSIM 5. We observed the highest number of completed trips when we use integrated control, and integrated control resulted in huge reduction in the delay of the arterial street, but of course with the cost at the travel time at the freeway, which was by 5%. So at this point, I'm gonna move to the next topic, which is development of a procedure for adjusting arterial signal control to reduce on-ramp demand. And I'm gonna ask Dr. Elefteriadou to continue.
Thank you much, Ali. So I'm gonna talk about a different approach that we used, which is more I would say not an optimization and not based on prediction, but more of a pre-timed calculation to figure out, are we able to reduce congestion on the freeway and the demand for the on-ramp if we adjust the signal control for the intersecting arterial. Next. So I won't go to all the details of what the methodology is, but the basic idea is we're looking at what is the capacity of the merge. We're looking at comparing over here on the left whether the on-ramp demand exceeds the capacity of the freeway. And once that happens, then we're looking at the amount of excess traffic that is on the on-ramp. Of course, all that assumes deterministic calculation. So we have to have a deterministic capacity for the merge, and we have to know in advance what the demand is for the ramp. So then once we calculate the excess traffic that arrives to the on-ramp, then we go through a procedure where we distribute that excess demand to upstream intersections that feed into the on-ramp. And I'm going to show you just a couple of case studies that looked at we actually looked at 3 different case studies. I'm going to share 2 of them with you. So what we're doing is we're comparing what happens to the delay or the average speed for the entire network, and then what happens to the queues upstream when we are basically holding up traffic upstream so that it doesn't get to the ramp and lead to breakdown. Next. So this is the first case study. This is exactly the same site that Ali already presented. We did the 2 case studies I'm going to share with you are, one is the full network, and the other is the truncated network, similar to what Ali presented. The site is in California. We also did a similar process for a 3rd case study in Florida. And I won't go through the results, but it's in our report. And that 3rd site is the one Mohammed's going to talk about later. So as you're seeing in this, sorry, if you go back, as you're seeing in this image, we have breakdown on the freeway already. So what we were able to do then is from the simulated site, which was in Vissim, we were able to extract a number for capacity at the merge. I'm not sure if you can see my cursor here, but where you can see the dots here with where the traffic is forming. And then the intersecting arterial, we have several intersections that feed into this loop on-ramp. And so we used our procedure to adjust the demand that gets into the on-ramp. Next. So I'm just going to show you the results for this particular case, and the figure here is showing on the vertical axis, you're seeing the queue length. This is for a freeway. Horizontal axis is the by time, and we had the simulated demands over the entire peak period. The blue line is showing the before queue length, and the after is shown in orange. So with our procedure, we were able to delay by several minutes the development of the queue on the freeway. Of course, as with any system, there's only so much you can do. If you have significant demand on a consistent basis, then sooner or later you're going to have a breakdown. But with this approach, we're able to delay it. Next. The next slide now is showing for the 3 intersections what's happening with the queues. So for the first intersection, which is at the top of your screen, you can see the comparison of the before and after. So clearly with the after, we have increased queue because we're holding back traffic, but not by such a significant amount. With the before, the queue started to develop closer to 130 minutes, but with the after, it started a little bit earlier. Length was consistently around 400 feet, which is, depends on where you are. You may be able to manage that depending on the length of the segment. Same kind of a comparison for the second intersection, the queue. Here, we were actually able to have pretty similar queues. It goes back and forth in terms of the length, and then during the majority of the time, the queue is pretty similar. And then for the third intersection, actually the queue was a little bit less. So not a huge change in terms of the queues observed on the signals, despite the fact that we were holding back more of the traffic, but then some improvement on the freeway. So in the next slide, I'm going to show you overall network comparison. So for this particular network, the average speed, considering the entire freeway and the arterial, on the average, things were better with the control for the signals. So Not a huge change, a few miles an hour for the entire network, but still overall, we were able to achieve better performance and improve the freeway operations by a little bit without significant impact in terms of queues for the upstream signals. Next one. Now the next network it's pretty much the same network, but it's more extended, and I think this is the one that's more along the lines of what Ali's team used. So we followed the same procedure, but because we had additional segments, then the breakdowns were at different locations. So the entire process actually was, the process was similar, the results were somewhat different. So I'm going to share with you just some numbers here with the after. So here you can see the average speed improved significantly for the with our new methodology. So depending on the network, you might have more significant improvements, and again, this depends on a couple of things: how extensive your network is and how far back you can start controlling the signalized intersection. So the closer you are to the merge, the less you can do in terms of holding back traffic. This is for the extended network. We were able to do more. Next one.
Yeah, thanks a lot, Lily. So the next one is our third topic point that we are going to talk about: machine learning models for predicting capacity reduction resulting from RAM queue spillbacks. And Dr. Hadi will be talking about these parts. Please.
Thank you, Ali. And our work is, as Ali said, is to predict the spillback before it occurs, such that you can apply methods to address that or mitigate that effect, such as the ones that Ali and Lily talked about. Next slide. So this network is the third network, or the second network that Lily mentioned. It's in Florida on near the I-95 facility, and it is basically now a segment of Northwest 119th Street, which is an important arterial. And we looked at the intersections in the vicinity of the interchange with the I-95 northbound and southbound. Next slide. So basically what we wanted to do is to look at using machine learning in predicting the capacity reduction due to spillback. And we use two models. One of them is categorical model that we estimate the percentage change in capacity based on three categories. And when we looked at the traffic or the reduction in capacity based on the data, we could see that three distinctive categories of reduction in capacity. So we wanted to have those as a categorical variable arranged basically for each of those drops in capacity. And for that, we used a decision tree model, and we fed the results into a fuzzy logic, fuzzy rule-based system model to consider that the decision tree results are crisp results, while in reality it can be stochastic. So the fuzzy rule can take that crisp and change it into a fuzzy. For the second type is LSTM-based recurrent neural network model for the categorical model. For the continuous models, we estimate the capacity reduction as a continuous variable, and we use the M5P decision tree models, and again, the LSTM recurrent neural network model. In the beginning, we included the flow rate at critical location, occupancy, a green occupancy ratio, and travel time as input to the model. But then when we were discussing with the researchers in the project, we said, okay, maybe the green occupancy ratio and the travel time are latent kind of variables. They happen after the spillback occur. So let's try to do the model without those and only include the flow rate at a critical location and occupancy of the, by the way, this occupancy is the occupancy at the on-ramp, at the Q detectors on the on-ramp, while the green occupancy ratio is at the stop line of the signalized intersection. Next slide. So again, we use a simulation model. We calibrated based on the real-world data. Because of the location of the detectors in the real world, they have high-resolution controller data and ATSPM data, but the problem is that the locations of those are not optimal for all the variables that we needed. So we decided to go with the simulation models, and we recommended changes to the configuration of the detectors. So the model segment included the 6 signalized intersection of Northwest 119th Street, and the model was calibrated based on the field data, as I mentioned. Next slide. And so we included the different variables that include, as I mentioned, the GOR at different locations and the flow rate and the queuing on the on-ramp and occupancy at the on-ramp and so on. And then the capacity reduction rate either as a category or as a continuous variable were the output from the models. Next slide. So when we run the models, they generally, when we look at the parameters that are normally recommended for testing machine learning models, they generally produce good results with the LSTM-based recurrent neural network, producing somewhat better results in terms of the standard machine learning model parameters. And we looked at it now further from a traffic prediction point of view, and those are confirming that the recurrent neural network produce results, as we're going to see in the next 2 slides. Next slide. So if you look at the time steps and you look at the prediction, this example of how we look at it. So for example, when you look at the continuous model with the M5P decision tree versus the RNN, you see that the red is the grounded truth, which is the real spillback and reduction capacity, while the blue is the prediction from the neural network, and the green is the prediction using the M5P. And you see that the blue is closer to the red in both when we use all the variables, and then when we exclude the green occupancy ratio and the travel time from the inputs, the differences even becomes higher. But it looks like clearly that the RNN is producing better results here. Next slide. And then when we look at comparing the categorical and the continuous model in terms both of the estimation, ability to estimate the category of the drop and estimate the actual value. When we compare it, we took the when we look at the continuous value or percentage error, obviously the categorical model will not be able to estimate the continuous value of the reduction, and so we assume that with the categorical model, it is the median is the one that we use in the comparison. We could see that the prediction of the category is better with the categorical model, but by little, not by much, 99.4 versus 96.8. But when you want to actually predict the continuous, the reduction as a continuous variable, the continuous model was able to predict the reduction as expected, better than the categorical variable, and that is 7.4% versus 24.7%. Next slide. So in summary, the models developed to predict reduction in capacity as a continuous variable provided better prediction of the capacity, and the LSTM-based RNN, recurrent neural network model, produced better results than the other models tested in this study. Excluding the green occupancy ratio and travel time, did not produce better result. In fact, this could be maybe a little bit deterioration in the results, but so it may be useful to include them. The difference is not that high between include them and excluding them. And I think that's my last slide.
Yeah, thanks a lot, Mohammed. In conclusion, there are really like 4 points that we want to highlight here. So the integrated corridor management yielded significant improvement in traffic operations in our case studies, and it balanced the delay between the main line and arterial streets. Adjusting the signals along the arterial using the procedures that was developed in this project improves flow on the freeway, and that is achieved with relatively small impacts on intersection queue lengths, which is really important. And we also found machine learning models able to predict the spillback from on-ramps to upstream intersections quite accurately with at least 2 cycles prior to the queue spillback occurrence. So really you have like 2 cycles to respond, and that also was one of the important findings here. So with that, I'm gonna go to like our one to the last slide, so questions and a survey that we have. So if you have any questions, please type them in the Q&A, and then we are going to read them and answer them. And there's also a survey that is going to be show up in the chat box. So if you don't mind, please take a couple of minutes to complete that survey too.
Yeah, if you could just put your questions in the chat, that would be great.
I see Mohsen raising his hand somewhere.
Yeah, I see that. Maybe I need to ask.
Yeah, if he could enter the question into the chat box or the Q&A.
Okay.
There we go. It popped up in the Q&A.
Awesome. So let me see. Please go to your slide that you solved your model. So Mohsen, do you want to see the solution technique that we talked about? Yeah, I can talk about that for a second. And I'm not showing like all the details of the solution technique here, but we are following model predictive control. So what that means is that we are observing the current state of the system, and that means that we are looking into VSIM, and we are looking at where vehicles are, and then based on that we feed that information to our cell transmission model and predict traffic state over a prediction horizon. That usually for us is several minutes. And when we do that, we run the optimization, we find the optimal signal timing parameters and ramp metering signals for the next 5 minutes, but we only implement them for the next few seconds. And when we do that, we enter them in Visim. And then we let Visim to go forward for those few seconds, and then we repeat this state over and over until the end of our study period, which here I think it was like 4 hours or so, either 2 or 4 hours, if I'm not mistaken. So I don't know if that's Mohsen what you wanted to hear. If you have any other specific question, please let us know. Yes, this question is that if we have used Visim in our solution, that's right. Yeah, our solution is implemented in Visim, and all the numbers that you are seeing are direct output from Visim. Any other question, please type them in chat or in Q&A. The question is that, is our first chapter published in a journal? No, we are in the process of publishing the paper, submitting the paper, so it's not published yet. So I have a question from Tahsin. GOR is dependent on the detection zone length. Did you include the length of the detection zone as a variable? And I believe this is for Mohammed.
Yeah, that is, we use a standard detection length that is recommended in the literature. So we did not. That's part of why we use the simulation. We use in the real world, some of those left-hand detectors are 50 feet detectors and so on, but we use short detectors to get reasonable values for the green occupancy ratio. Otherwise, we would have our initial intention was to use the real-world data, but that and a couple of other reasons of the detection configuration made us decide not to go with real-world data and use simulation for it, for the training, or for obtaining data for the training.
Thank you. Michael has a question. I learned from visiting LA to not get in the westbound queue from Sunset to I-5, but to go through the intersection and approach the I-5 interchange eastbound. Does this behavior get evaluated in this study? I don't believe that we directly address this, like we are not accounting changes in OD here, but the input to our system, if that traffic demand that is input to our system already showing this, then it is accounted for. But if it is not included in the demand that is entering or is entered into the simulation here, we are not accounting for it. Musa is asking to go to the results that you have compared 3 things in your model. Musa, which slide do you want me to go? Is this the one that you have in mind? Okay, so this is not the one. How about this one? Okay, so what's the question? So I'm just waiting for Mohsen to type in the question. In the meantime, if there is any other question, we are happy to answer. Did you overall decide which approach better? So do you mean if we said which approach among these is going to work better than the other one? Well, it depends on your objective. If you want the most balanced performance, integrated corridor management is going to give you the most balance in performance. If you want the best performance on the freeway, you can use integrated corridor management with different weights in the objective function so that it increases the importance of the freeway, or you can see that the existing method that is there is going to give you also a very good performance on the arterial on the freeway. But it really goes back to what you would like to achieve. So optimal signal control, for example, gives you the best performance on the arterial, but on the freeway the delays are a little bit more. And also we need to keep in mind that the numbers that we see here are coming from a case study. As you saw on Lily's presentation, when you extend the size of the network, some of the results that we observe could change significantly. Okay, sure. Is there any other question? So while we are waiting for any other question, the next webinar on STRIDE is, I believe, tomorrow: transportation, disadvantaged populations, travel characteristics, and emerging mobility solutions. And I believe that there is going to be a link for registration on the chat box. If it's not there, it's going to show up very soon. And so I want to thank you all for attending this webinar. If there is no any other question, we would pause here. So I'm gonna check with Lily and Mohammed if there is anything, any last minute thing that you would like to discuss. If not,
None for me.
good to
Thank
go.
you.
All right. How about you, Mohammed?
Not from me. Thank you, Ali.
All right. Thanks a lot. Thank you all, and have a great rest of the day.